Hi friends, our next topic is diffraction. You observe in this figure, when light enters through this hole, it is supposed to go like this, right? Just as it entered. But you see that some part of it is bent this way and this way here. That bending is known as diffraction, and it is a common phenomenon observed with sound waves as well as transverse waves. But it is less pronounced when it is the case with light because the wavelength of light is very small, right? That's why you see when a wave passes through a slit, it even bends here, and this diffraction accounts for the interference pattern observed in an experiment which is something similar to Young's experiment, Young's double slit experiment. We'll do the same experiment with a single slit now. When you do it with a single slit, this is what you observe. At the center of the screen, a very big bright fringe is seen, and as you go farther from the center, you see fringes, but they are less intensified as you go further away. And let's try to give some explanation to this. And it is also found that the minimas are found at n lambda by d distance from the center, and the maximas are found at n plus half lambda by d distance from the center. Let us try to give some explanation for this also. The basic idea is to divide the slit into much smaller parts and add their contributions for some point P with the proper phase difference actually, because observe this, here the wavefront was coming right. So till these 3 points, all the three, actually there are many waves inside it. Let's consider three of them, and all these were in phase till these points. For a point P which is at very far distance from the slits, I can consider these rays to be parallel. Observe that this rays got bent, say by an angle theta, and theta is going to be very less. So this will also be theta, this will also be theta. Now let this point be L and the midpoint of the slit be M, and let this be N. Now what is my phase difference for these two rays, LP and NP? My path difference will be NP minus LP, right? Observe that till LMN all the three rays were in phase, and the path difference is LP will be equal to, say if this point is some Q, that will be equal to QP. So this ray, the bottommost ray, has traveled an extra distance NQ, and that will account to a phase difference. So similarly, all the waves which are coming here, they are not in phase, and observe that they are coherent still. They are coherent, but they are not in phase. Observe one thing, this is theta, right? So this will be 90 minus theta, and hence if I join LMN, this angle NLQ, that angle will be theta, na? Angle NLQ, that is theta. So from this right angle triangle LNQ, what can I say? My sine theta is nothing but NQ, which is the path difference, NP minus LP, by my, let the width of that slit be A. So A sine theta will be my path difference, right? If theta is very small, I can consider sine theta as theta. So this is my path difference, NP minus LP. And similarly, for any two points inside the slit which are separated by some distance y, say, the path difference between those two rays coming from those 2 points will be y theta. Hope this is clear. Now let's move forward. Actually, we have to sum up the equal and coherent distributions from a large number of sources, right? Because even though this is a very small slit, there are many, actually millions of waves coming from it. So we have to sum up all the contributions at the point P, and each of these waves is having some different phase, or the phase difference between each of these two waves is different. So summing up it is a very difficult thing. It is done by integral calculus, so we are not doing it here now. However, we'll discuss some main features of this diffraction pattern, like bright spots and dark spots. First of all, experimentally it was found that when theta is equal to 0, that is when this angle is 0, that will be the center of the screen, right? Intensity was found to be maximum there, and for all the thetas which are given by n lambda by a, where n is plus or minus 1 or 2 or 3, that for all these thetas, it was found that intensity was minimum, that is a dark spot. For all those thetas which were approximately given by n plus 1 by 2 lambda by a. For all these thetas, it was found to be a bright spot. Now let us try to explain each of these. This case is simple. When theta is equal to 0, it is at the center of the screen, right? So this wave and this wave add coherently, and this wave and this wave add coherently, this wave and this wave, and hence all the waves pretty much add coherently. So you have the brightest spot here, that is maximum intensity is found here. Now, next we'll discuss this case about dark spots. They are found when theta is given by n lambda by a, of course, approximately. Now, what happens here? Observe this. I know that my path difference is given by a theta. We just discussed it now. If that will be equal to lambda, what happens? Or more generally, take if theta is equal to lambda by a, that is, I put n is equal to 1 in this equation. For that case, observe this. This is my slit, and say rays are going in this way, and consider a midpoint m. This is theta, right? If my theta is lambda by a, then what happens? There are many rays coming from many points here and here also, right? So consider any point m1. Here it will be giving a ray in this direction. So I can find a point m2 in this region such that m1 m2 is equal to a by 2. Is this fine? Because this is L and this is midpoint m and this is n. The whole fringe width is a. So for every point m1 in Lm, I can find a point m2 which is at a distance of a by 2 from m1, so that the path difference of those waves given out by m1 and m2 will be equal to y sine theta, right? Y is what here? A by 2, and theta is what? Theta is lambda by a for this case. So if theta is lambda by a, the path difference between these two will be lambda by 2. This corresponds to a angle, a phase angle of pi, right? So this is a destructive interference between those two waves. But what? M1 is any wave or any point between L and M, right? So for all the points between L and M, I can find corresponding points between M and N such that they sum up to give 0, that is destructive interference. So for this angle theta, which is given by lambda by a, I'm going to get a dark spot. Now you may ask, theta is lambda by a, then it's fine, you are getting a dark spot. How can you say that when theta is n lambda by a, for all n's you are getting a dark spot only? Observe this. I'll again take the slit and say now my theta is n lambda by a. If take 2 points, again I'll divide this into L, N, and this is midpoint M, right? Okay, for some point M1, I'll get a point M2 which is at distance a by 2. Then my path difference of those two waves given by M1 and M2 will be a by 2, and theta is n lambda by a, right? So it will be n lambda by 2. This may correspond to that phase angle which is giving destructive interference, or it may not also. Observe this. If n is any odd number, say 3 or 5, that will give destructive interference. But what if n is 2? Then it will give lambda, right? So you may think that here it is not the case, but actually it is. Observe this. Now M1, M2 are giving out two waves whose path difference is lambda, right? So I can again divide this into two intervals, and this case is something similar to what we solved before. And again I can find two points M11 and M12 inside them, so that the resultant of these two interferes destructively, and so the entire contribution of M1 and M2 will be 0, and hence M1 and M2's contribution is 0 means M1 and 2 can be varied between this whole slit, right? So that means that entire slit's contribution is 0 in this case also, where n is equal to 2. And similarly we can prove that for 4 also, for 6 also, for any n. Just you have to go deeper and deeper if n is large. Now this is not for any n actually, because if n is equal to 0, you have that center bright spot, right? So for any n except 0, this holds true. I mean, if that theta is equal to n lambda by a, you're going to get a dark spot. What about white spots? They are given by n plus half of lambda by a, right? Consider this case where the slit can be divided into three parts. Say this is L and N. So for n is equal to 1, I'll get my theta to be 3 by 2 lambda a. For that case, I'll consider this part Lm2, which is equal to 2 by 3a. So the waves given out by L and M2 at those points, their phase difference or their path difference will be 2 by 3a into 3 lambda by 2a, right? Which is equal to lambda. So it is something similar to previous case when you have 2 points and giving out rays, they can be divided into two halves if their path difference between these two rays is lambda. The halves get cancelled, right? So all the waves between these 2 points, they get cancelled. I mean, destructive interference takes place, and finally it is equivalent to that case where where intensity is given only by 1/3 part of slit. And don't think that intensity is given by the bottommost 1/3 part. Actually, it is given uniformly. I could have taken this part m1n and showed that I could have shown that the intensity is destructively interfered between these 2 points m1 and n. So I can also say that 1/3 intensity, that's what you are seeing, right? That is given by the upper 1/3 part. So it's not actually given by any part, it is given uniformly. Note that this is just a way to get intuition. That's not what exactly is happening there. Actually, it will be better if you do it by integral calculus, because that's cumbersome, we are not doing it. This is just a way to get intuition, note that. And the intensity will be even more or less if n is equal to 2, then it will be 1/5 of the slit, I guess, and 1/7 if n is equal to 3, and so on. Hence the intensity is decreasing as you see in this graph. Say this is your bright part of the diffraction. Here you got dark spot, right? Dark spot. So by the formula we have just seen now, the dark spot is this one. This theta will be given by lambda by a, first dark spot, and hence the 2 theta will be, this will be the broadness of the central bright fringe, the angle subtended by the central bright fringe. And you might have observed that diffraction is something similar to interference. Actually it is. You just use the term interference when you have two sources like double slit or something like that, and you use the word diffraction when you have many sources, like even though it is a single slit, we are considering many light rays coming from this slit, right? And that's why it is just a usage of terms in different cases. Actually, even in double slit case, you see the diffraction. I mean, diffraction takes place even there also due to each single slit, but you won't be able to observe it clearly. Actually, what happens is this is the diffraction curve. What say this upper curve, broader curve? This represents the central bright fringe, this part, and this represents the next bright fringes. That is, these represent the secondary bright fringes of diffraction, and the inner peaks, they are the normal or those fringes due to the double slit experiment. So when you have a double slit, what happens is both of them are seen, but this central bright fringe is so large that it will be something like this, and inside itself you might have seen many bright fringes of the of those due to double slit experiment. The number of bright fringes inside one broad diffraction peak, this peak, is given by d by a. It's proportional to d by a. So actually it is okay. Let's discuss one problem so that you'll understand it better. What should be the width of each slit to obtain 10 maxima of double slit pattern within the central maximum of single slit pattern? We just now discussed that if this is the dark spot in diffraction case, this theta is given by lambda by a, right? So the net angle subtended by the central maxima in diffraction case will be 2 lambda by a, and that should be equal to the 10 times. We have to have 10 maximums, right? And each angle subtended by one fringe is lambda by d. We have discussed this before. So this is your equation. What I'll get, my d by a should be equal to 5. The distance between two slits, that is small d, is given as 1 millimeter. 1 millimeter. So you will get a as 0.2 millimeters. This 10 is the number of maxima inside the broader fringe, right? That is due to diffraction. So I can generally say that 2d by a is the number of smaller fringes inside that bigger fringe. Note that this is independent of wavelength as well as distance between the slits and screen.